Okay. Are we live? I think we might be live. Ha 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 ha. Let's see if I can. Sorry. Mr. Kitty is a little excited today. Sounds like he's very eager to participate in all of this. Okay, so once again, I'm going to do a little bit of stalling while I wait for, well, let's call it giving people a chance to arrive if they wish to. But yeah, welcome to the lecture. Happy to have you all here today. Very excited to be here. Today, we're going to be talking about probability. Some updates, though, before that. Let's see. So I mentioned earlier that I probably will have to put these lectures on pause for a bit. It looks like we have today, Wednesday, and then one more scheduled for next week. And then after that, I'm afraid that I'm going to have to put these on pause for a little while because, like I said, last lecture, I think my job at my other university got busier than anticipated. Let's put it that way. Yeah. So I am going to have to hold back on this for a while, unfortunate, which stinks, but you know, it is what it is. So we're going to do our best. We're going to do our best. And that's all anyone can ask of us. Yeah, today we're going to be talking about probability. This is actually like it's going to be a two-part lecture. There's going to be a bit more about probability on Wednesday. We're just going to sort of start going into it. As far as calculating probability is concerned, we're not really going to go too in-depth into that kind of thing. I just mostly want you to understand how it works, all that good stuff, you know, like things like what does it how do I put this? You know, fallacies associated with probability, general thoughts about how probability works, what it looks like, all that good sort of thing. That's more or less what we're going to focus on today. Okay, so current plan. I think we should be pretty much ready to start the lecture soon. It's very exciting in my humble opinion, which is maybe not so humble. Maybe I should be a bit more humble. Oh. I hope everybody's surviving the school year so far, by the way. I'm surviving as much as I possibly can. You know how it is. Different things happen, things pop up unexpectedly, and that's not just true for students, that's true for the teachers as well. Okay. I think I'm gonna hop over to the lecture. Here we go. Here we are. We're talking probability today. Let's see if I can. Hey, yep. I wanna put myself over here. I think that might be a better place to put myself today. Hopefully that. Okay, let us get rolling. So, probability, like I said, we're talking probability today. Now, first things first, I want you to consider whether you have ever played some sort of game of chance, which is like super, super broad, I know. I'm talking about things like gambling, cards, loot boxes in video games, any type of gacha game, random mechanics. There's a lot of random mechanics in a lot of different video games. Like Minecraft has some random mechanics in terms of like drop tables, punching rocks in Animal Crossing, all that kind of stuff. Any sort of like game or activity where there is some element of randomness. If you have done that, you've probably fallen for something called the gambler's fallacy. The gambler's fallacy is a logical fallacy that says that past random events will influence future random events. So it's believing that things that were random in the past will influence things that are random in the future, when, by definition, these random events are independent from one another. The outcome of one random event has absolutely no bearing on the outcome of another random event. And I know that's kind of abstract, so we're going to go into examples. Shiny Pokemon. So I play a lot of Pokemon. I don't know about all y'all, but sometimes I do like to hunt shinies from time to time. And in the more recent games, so the odds have changed, but in the more recent games, I believe, is this a screenshot from the Scarlet and Violet? looks like violet based on the uniform. The probability, or base odds, as I think shiny hunters call it, of catching a shiny Pokemon without any modifiers whatsoever is 1 in 4,096, or about a 0.002% chance of finding a shiny. That's just finding one, that's not necessarily catching one. So in this image above, we can see an example. Here is a crowd of Espeon, and you can see the shiny one, shiny Pokemon, sorry, if you weren't aware, are Pokemon that are a different color than others of their species. That's pretty much the only special thing about them. They aren't different in stats or anything like that, but because they're so rare, people like to collect them. So there's very, very, very low odds of just encountering a shiny random. Now, things that might happen if you're falling for the gambler's fallacy. First, if you're falling for the gambler's fallacy, you might believe that a random event is more likely to occur because it hasn't happened for some period of time. So for example, I haven't seen a shiny Pokemon in weeks, so I'm definitely going to see one today. Or you can also think about this in terms of gacha games. I haven't rolled a super rare character in months, and therefore I'm due to roll one soon. Another version is a random event being less likely to occur because it hasn't happened for a period of time. So, for example, I have bad luck, I'll never see a shiny Pokemon, or I'm on a losing streak in terms of gambling, or I have really bad gacha luck, I will never roll something good in the gacha. Another version of this fallacy is thinking that a random event is more likely to occur because it recently happened. I'm having great luck today, I just saw a shiny Pokemon and I bet I'll see another soon. Or in terms of gacha games, I just rolled a SSR character, I rolled a super, super rare character. I have great luck today, I better keep rolling, I don't want to waste my luck. And then of course, the version a random event is less likely to occur because it recently happened. This is the version that I in particular am most susceptible to. So this is, I just saw a shiny Pokemon, there goes my luck for the rest of the week. Or, I just rolled a SSR character in the gacha, I need to stop now because I've used up all of my luck. I'm not going to roll another one again. I believe on Twitter, actually, I made a tweet about the gambler's fallacy somewhat recently. I play Pokemon Go, and I actually ran into 2 full odds shinies right in a row, and I nearly hadn't checked the second one because I was like, well, I just found a shiny. That means clearly the next Pokemon I check couldn't possibly be a shiny, but that's the gambler's fallacy. Those are 2 completely random events. They are not related to one another in any way. So it is just as, well, it's not just as probable, but it's not improbable or impossible for me to encounter 2 shinies in a row. And that's not because of luck, that's just because of how random events work. So long story short, the gambler's fallacy, which if you can't tell by the fact that it's called a fallacy, is incorrect, is the idea that these past random occurrences influence future random occurrences, whether that's rolls in the gacha, whether that's checking shiny Pokemon, whether that's playing slots, whether that is opening loot boxes. The past random events do not affect future random events. Other biases according to probability. See, the human brain really is not wired to think in terms of probability. We really struggle. Our brains try and see patterns. So especially when it comes to random events, our brains struggle with them. So there's the gambler's fallacy, the belief that past random events influence future random events. Then there's equiprobability bias. This is this assumption that random events are equally probable by nature. So on the right, I have a meme that a lot of students tend to send to me that I absolutely love. There are no probabilities other than 50-50. Either something happens or it doesn't. That's equiprobability bias. So for an example, since everything's random, I'm just as likely to see a shiny Pokemon as a normal Pokemon. Or I either roll an SSR or I don't, and therefore there's an equal chance of rolling an extra rare character as there is a common character. That's equiprobability bias. Those are kind of extreme examples because these are very rare occurrences, encountering shiny Pokemon or rolling an SSR. But the general idea is that 2 events are equally likely to happen just because they're both random. And that's not necessarily the case. Some random events are rarer than others. Then there's the representativeness heuristic, and this one, I think it's easier to explain by using an example, but I'll use the sort of generic definition of it first. This is another fallacy, another false belief that we tend to hold about probability, that samples that correspond with the population distribution are more probable than samples that don't. Which, again, I think describing it abstractly like that isn't super understandable. I think the easiest way to understand this is with coin flipping. Assuming that you have a fair coin, you have an equal chance, a 50-50 chance of getting heads and tails. So it's kind of easy to assume that if I flip a coin 10 times, I'm more likely to get 5 heads and 5 tails than I am to get 3 heads and 7 tails. But that's not true. Both of these outcomes, assuming you only flip the coin 10 times once, so you only do this once, both of these are equally probable. It's not 50-50 exactly on a single set of 10 is more probable than a 3-7 split. They're both equally probable, assuming that you're only doing one set of 10 flips. Other misconceptions. We often have misconceptions about probability because of beliefs we hold. So we might believe that the eventual outcome of an event depends on a force beyond our control, which often this manifests in the term of luck. So believing whether I find a shiny or not depends on my luck. I see people say, I have really bad luck in the gacha, or I have really bad luck with shiny. Or I like to think that I have fairly good luck in gacha games. I usually, I'd say more than half the time, I get who I want. And so I tend to consider that I have very good luck, but luck isn't a real thing. This is all random. You can also think of this as like, sometimes people will say, I'm favored by the gods, or like in fiction or in real life. That is also one of these forces that is out of our control. As far as this class is concerned, as far as statistics and probability are concerned, that's not a real thing. It's a belief that we have, but it doesn't actually reflect the reality of probability. Then there's things like human control, which is the assumption that you can somehow control the outcome of some random event. So if I do a little dance before I roll the dice, or if I hold my switch at a 45-degree angle, I'm more likely to find a shiny Pokemon. With Pokemon in particular, I know for a while, when you're trying to catch a Pokemon, there is some randomness involved in whether you successfully catch a Pokemon. And there's a lot of factors, but randomness is one of those factors. And there was this rumor floating around that if you just kept pressing the A button on your Game Boy, it would make you more likely to catch them. That's not the case. This might be like, I'm wearing my lucky socks today, so I have tried to exert some control over the outcome of this random event. All these things are misconceptions as far as the way that we think about probabilities concerning statistics. But the human brain likes to think these ways. It's not a surprise that these are very, very common beliefs. And that means when you're thinking about probability, you've got to be very, very careful about how you're thinking, because our brains don't think this way by default. Be careful. Now, I'm going to ask you a question, and this is not a trick question. Okay, I'm going to tell you ahead of time, this is not a trick question. If I ask you a trick question, I will tell you that it is a trick question, okay? Where'd my window go? Okay. So here's Misaka from a certain magical index and a certain scientific railgun. Anyway, here's not a trick question. Misaka flips a coin 20 times. She gets heads all 20 times. If she flips the coin again, what is she most likely to get? Heads, tails, or an equal chance of heads and tails? Based on all that we just learned. I'd like you to think about that to yourself for a minute. Be more likely to get heads, tails, or an equal chance of heads or tails. Assuming that, the last 20 times she flipped, she got heads every time. And we're going to assume that this is a fair coin. It's not weighted. The correct answer is an equal chance, right? If you answered heads or tails, you're probably going into the gambler's fallacy. Each coin flip is an independent random event, so the outcome of the past 20 flips has absolutely no bearing on the outcome of this flip. There's still an equal chance of heads or tails, assuming that this is, a fair coin. Now, I said I wouldn't ask you trick questions, but I'm going to ask you one trick question, but I'm warning you that it's a trick question. So keep in mind, I'm looking for what you the intuitive answer is. The intuitive answer is going to be wrong, but if I ask you, say, you just met with your doctor, and the doctor has informed you that you have tested positive for a 100% fatal disease. So if you have this disease, you will die, and you've tested positive for it. To make things worse, the test that they used is accurate 95% of the time. What is the probability that you will die? Think about that for a second. Now, if you're thinking about the intuitive answer to this, the intuitive sort of knee-jerk answer that a lot of people have is 95%, or there's a 95% chance I'm going to die. This disease is always fatal. The test is accurate 95% of the time, which means that if it says that I have the disease, there's a 95% chance that I actually do have the disease and will die. That's the intuitive answer. But the thing is, like I said, this is a trick question. According to the laws of probability, that is not necessarily the answer. There's additional information that I did not give you that's necessary to figure out the real answer to this. What you just did is called the base rate fallacy. We tend to judge the probability of events, but we might not necessarily take into account how common those events or the probability of those events just at a base rate. How probable or improbable is that event? Again, I think this is another thing that's way easier to explain with concrete examples. So let's look at this table down here. Let's say that we look at, what is this, about 10,000 people who take this test for this disease. This disease is actually a very rare disease. It's very unusual. Only about 100 people out of 100,000 people actually have this disease. So it's very, very rare. It's very unlikely that a random person would have this disease if you just pick them up off the street. Of the 100 people who actually do have the disease, again, this is a 95% accurate test. So 95 of those 100 people, they test positive and they do have the disease. And 5% or 5 of those people, they test negative, but they still have that disease. That's that 5% error rate. But the thing is, the vast majority of people who take this test, something like 99,900 people, do not actually have this disease. Most of the people who are getting tested for this don't actually have the disease. And they also have that 95% error rate. So that means 5% of them are getting told they have the disease when they actually don't. And 95% of them are getting told they don't have the disease when they actually don't. So there's still a 5% error rate. It's still wrong 5% of the time. But because almost everybody taking this test doesn't actually have the disease, there's a lot more people. There's nearly 5,000 people testing positive for this disease when they don't have it, because there's that many more people who don't have it who are taking this test with the 5% error rate. So in reality, because the base rate of the disease is so low, because the disease is so rare on its own and so many more people are being tested than actually have it, testing positive on this test for the disease actually only means you have about 1.9% chance of dying from this disease, or that you actually have it, because so many more people who don't have it are getting tested, and there are false positives there. A lot of people, even though it's only 5%, a lot of people who don't have the disease are testing positive because of that 5% error rate. So if you just look at that, yeah, it's actually still, based on a singular test, a relatively low chance that you actually have the disease and you're going to die, because the base rate of the disease is so low, because it's so uncommon relative to the population. This is why back during the pandemic, I think I can say these words, I'm not monetized anyway. Back during the pandemic, this is why if you tested positive or if you tested negative, essentially if you took one COVID test, they told you to take multiple. They're like, okay, if you test positive, test again just to be sure. Or if you test negative, test again just to be sure. Because they had error rates. The more times you test, the more of a chance that you're gonna the less of a chance that all of those tests will have a false positive or false negative. They want you to test multiple times because they know these tests aren't perfect and that the base rate might screw things up. So that's the base rate fallacy. Another example that I think is even easier to digest, here's a XKCD comic about the base rate fallacy. It says, remember, right-handed people commit 90% of all base rate errors. Why do you think that right-handed people commit 90% of all base rate errors? Do you think it's because right-handed people are more prone to believing in the base rate fallacy? Or do you think there might be some other reason? I'm gonna give you a few seconds to think about that. It is indeed that 90% of people are right-handed. That's it. 90% of people are right-handed, 10% of people are left-handed, 90% of people make base rate errors, 10% of people don't. Right-handed superiority. This is saying that you have that you're more likely to make the base rate error if you're right-handed, or at least that's what it's implying, but because, of course, of the base rate error, you know, it's not actually the case. It's everybody is equally likely to make to commit a base rate error. It's just that there are more right-handed people than left-handed people. Oh, no. I mean, I imagine it does kind of suck to be left-handed in a world that caters to people who are right-handed. Can't relate! I'm sorry, left-handed people. I'm so sorry. Anyway, yeah, there's your base rate fallacy. I'm going to do it one more time. I'm going to describe it this time in terms of gotchas and loot boxes. So I play Fate Grand Order. And let's say there's an event. There is currently an event in Fate Grand Order NA. I actually rolled the gotcha this morning. I am not immune to gotcha. Anyway, let's say you want a limited edition super rare item or a limited edition super rare character. Right now, I think it's is his name Yamanami? There's an SR Saber that's currently on rate up. Now, typically in Fate Grand Order, your chances of getting an SR character on a single roll is about 5%. So you might think that your chance of getting a limited edition SR character is 5%. You'd be wrong. FGO's mean this way. I think a lot of gacha games do this. It's your chances of getting that character, that SR Saber that just came out this morning, are not actually 5%, even though the chances of getting a SR character is 5%. See, in FGO, I think they've actually changed the probabilities since I last looked at them. But if you get an SR character in the gacha, there's only a 60% chance that that SR character is one of the limited edition SR characters. So it's not that you have a 5% chance of getting it. It's if you get that 5% chance, then you only have a 60% chance that you get the character you want. So really, if you are rolling for a limited edition, so event exclusive SR character in Fate Grand Order, you only have about a 3% chance of getting them. I got him. I got really lucky this morning. I shouldn't believe in luck. That's part of the gambler's fallacy. Yeah, it is kind of a scam. They have instituted a pity system, but it's not a great pity system. Everybody should be very careful about playing gachas. Do as I say, not as I do. I am largely free to play, so maybe it's okay. But yeah, be careful with gachas. They specifically are aware that people have these biases when thinking about probability. They're aware of the gambler's fallacy. They're aware of the base rate fallacy. And they are aware that human beings, our brains are not good at processing information about probabilities. And they use that to their advantage to make lots of money. It is not great. Oop. Oh, wow. Wow, what have I done? We are not at the end. We are not nearly at the end. My goodness, I accidentally skipped ahead. There we go. There we go. That's where we're supposed to be. I was trying to give myself this to just demonstrate how distressing everything was, and I did some silly things, it seems like. Oops. Okay. Alright. We're back. So, some rules of probability. Let's go over this. We might wonder what the probability of any two events are occurring are. So let's say we want to know the probability of A or B happening. So we're rolling a six-sided die. I am clarifying, if I'm talking about dice in this lecture, we're talking six-sided die. We're all nerds here. Oh, I'm sparkling all over the place. I need to stop sparkling. I've forgotten how to stop sparkling. There we go. I just turned every toggle. This is incredible. Okay, there we go. So let's say we're talking about a six-sided die, and I want to know the probability of rolling a 1 or a 2. So I'm only going to roll the die once, and I want to know the probability of getting a 1 or a 2 on that single roll. Well, the way to calculate this is the probability of getting A plus the probability of B. I don't care if I get a 1 or a 2, I just want one of those results. So the probability of rolling a 1 on a six-sided die is 1/6. The probability of rolling a 2 on a six-sided die is also 1/6. And there's no case where you get both a 1 and a 2. You roll a die once, you only get one number, so we don't need to worry about that bit. So I take that 1/6 probability plus another 1/6 probability, add them together, And I get 2/6, or 1/3, or about a 33% chance of rolling a 1 or a 2 if I roll a 6-sided die once. Then there are cases where you might not necessarily have a mutually exclusive probability. So let's say I want to know the probability of rolling an even number on the die or a number less than 5. The probability of getting an even number on a die is 3 out of 6. So there's 3 even numbers on a 6-sided die. There's 2, 4, and 6. Ooh, I gotta move myself a little. Ah! There's 2, 4, and 6. So there's a 3 out of 6 chance of rolling an even number. Then the probability of rolling a number less than 5 is 4 out of 6. There are 4 numbers out of all the 6 numbers on a die that are less than 5. So we could just add 3, 6, and 4 out of 6, but that's going to add up to more than 100% because we're counting some of those numbers twice. 2 and 4 fall under both even numbers and numbers that are less than 5. So that is counted for twice, so we want to subtract that so we're not counting rolling 2 and 4 twice. This adds up to a total probability of 5 out of 6. 5 out of 6, the numbers on a die are either even or less than 5. So there's about an 83% chance that you will roll a number that is either even or less than 5. There's only one outcome where you wouldn't get. Then we can also look at something called conditional probability. And again, I'm not going into too much detail about this because you don't need to understand it too in depth for the rest of the statistics, but I figured it's important to go over it at least a little. So let's say we're talking about the probability of A happening and then B. So conditional probability, one thing has to happen first and then the second. So let's say you've got a deck of cards. Well, first of all, one thing that you got to consider is whether these events are independent or not. So let's say, again, like you have a deck of cards. If the events are independent, that means after you pull the cards out, you put them back in. The first event does not affect the probability of the second event. I also think about this a lot in terms of music. So different music apps have different ways of dealing with shuffling. Shuffling with replacement is those music apps that will play your playlist endlessly. Every time a song ends, they queue up a new one. They keep going and going and going forever. Once a song plays, it doesn't get thrown out of the playlist. It just gets put at the back, or it gets put back into the pool of songs that the playlist could randomly play. And this is why when sometimes if you're listening to a playlist on shuffle, you will hear the same song like twice in a row or really close to each other. It's because after a song is played, it goes right back into the queue. On the other hand, so let's say if we're talking about a deck of cards, this would be the probability of drawing a heart and then another heart. You draw one card and then put it back in the deck and then draw another card. So you've replaced the card in the deck. A standard deck of cards has 52 cards. So the probability of pulling a heart in the first place is 1 out of 52. The probability of pulling a heart the second time, there is still 13 hearts, there's still 52 cards because you put that card back, is still 1 out of 52. So you have to take the probability of pulling a heart the first time and then multiply it by the probability of pulling the heart the second time. So that's about, man, I'm talking about this all weird. It's not 1 out of 52, of course. There are 13 hearts cards, 1/4. Each time it's a 1/4 chance. Hearts make up 1/4 of a deck of cards. So you have a 1/4 chance of pulling a heart the first time, then you put it back in, and there's still 1/4 of the cards are still hearts, so you have a 1/4 chance the second time as well. Multiply those together, and the probability of pulling 2 cards with the same suit in a row are about 6.25%. Then there's sampling without replacement. This means, let's say if you're working with a deck of cards, you pull out a card, and then you don't replace it before pulling the second card. Or to put this in terms of playlists, these are the shuffled playlists that do end. Once a song plays, it doesn't go back in the shuffle. Eventually, you're going to run through all the songs on your playlist, and it will end, and then you'll have to restart the playlist. That's shuffling, or that's sampling without replacement. And those events are not independent because the first card you pull or the first song you play affects the probability of the other songs. So let's say I pull out a hearts card. So I pull out a card and it's hearts. The probability of pulling that first hearts card out is 1/4, because there are 13 hearts out of the 52 card deck, 1/4. But now I have removed a card from the deck. Now the deck only has 12 hearts cards and 51 cards total. So the first probability is 1/4, or 13 out of 52. But after I've removed a card and I haven't put it back, the probability of pulling a hearts again is 12 out of 51. There's one less card total, and there's one less hearts card. So in that case, if I don't replace it, if I'm sampling without replacement, the probability shrinks to only about a 5.9% of pulling 2 hearts in a row. So when you're calculating probability, you need to consider replacement, and also when you're shuffling your songs, whether you have replacement on will determine if the same song plays twice in a row, and also if your playlist will eventually end. It affects probability, especially conditional. Now, that might have been a bit brain-bendy, but I promise some rules of probability are intuitive. I said the human brain isn't good at thinking about probability, but there are some things that it can handle. So, for example, let's say I have a 6-sided die. There are 6 possible outcomes on the die. So, if I roll the die once, what's the probability I will get a 2? Well, there's 6 possible outcomes, right? And 2 is only one of those 6 possible outcomes. So, if I roll a 2, if I roll the dice once, the probability of rolling a 2 is 1/6. 1 out of 6 outcomes is the one that I'm looking for. There's a 16.7% chance that I will roll a 2. All right. That's fairly intuitive. It's not all brain bendy. It's not all headache inducing. So, just a bit of review, just to check in. Let's say you have a deck of cards, and you draw a card and it's spades. You don't put it back in the deck, so you are sampling without replacement. Then you draw another card. What is the probability that your new card is also spades? So I'm not talking like the probability of pulling 2 spades in a row. I'm talking about what is the probability of pulling a spades, assuming that you have already removed one of the spades from a deck? Well, if you've removed one, there were 13 spades, now there's only 12 spades because you've removed one. And there's only 51 cards now because you removed a card. So you take 12 divided by 51, so 12, the number of spades left in the deck, divided by 51, the number of cards left in the deck, and your probability is 23% of pulling a spades after pulling the first one. If you do assume replacement, you do assume that you put the spades back in the deck, the probability stays 25%. But if you don't, it shrinks to 23% because you've removed a spade. So, you might be asking yourself, how the heck does all of this relate to what we've been talking about so far? How does this relate to frequency distributions and things like that? So I'm going to try and tie it all back in. So first, here, we have 6 boxes here. What is the probability of selecting the black box? You can tell me either in percent or in fraction. There are 6 boxes. One of them is black. So the probability of randomly selecting the black box is 1/6, or 16.67%. Here's another one. This time you have 4 boxes. 2 of those boxes are black. What's the probability of randomly picking a black box out of these 4 boxes? 2 out of 4. 2 out of 4 of the boxes are black, so the chance of randomly selecting a black box is 2/4, or 50%. Here's another one. Got another 4 boxes. What's the probability of randomly selecting the black box? 1 out of 4 of these boxes is black, so the chances of randomly selecting the black box is 1 out of 4, or 25%. Here's another one. This is 10 boxes, and one of them is black. So what's the probability of randomly selecting the black box out of these 10 boxes? 1/10, right? Or 10%. Is this starting to look familiar? I hope it is. Now what? There are 36 boxes total, and 6 of them are black. What is the probability of randomly selecting the black boxes? 16%. 6 out of 36, 16%. Hopefully this looks familiar now. This should look like one of those frequency distributions we've talked about. Specifically, it should look like a normal distribution. Tall in the middle, gets shorter as you go off to the sides, symmetrical. Unimodal symmetrical distribution. This is where probability comes into this whole picture. We are going to use frequency distributions to estimate the probability of certain scores or the probability of getting certain outcomes. So, we talked about z-scores last time. Let's talk about how we can use z-scores in conjunction with probability to make judgments about things. So this is that z distribution that we had last time. It's nice and normal. The mean is 0. Exactly 50% of scores fall below the mean. 50% of scores fall above the mean. Yeah, the mean's 0, standard deviation's 1. So in a distribution like this, a normal distribution where the mean, the median, and the mode are identical, the tails go into infinity in theory, with extreme values, extremely high or low, being rare. Oh, sorry about the sirens. And the total area under the curve adds up to 100%. So the total area the total probability of randomly selecting a score in this range should add up to 100%. The probability of randomly selecting a score below the mean is 50%. The probability of randomly selecting a score above the mean is also 50%. Before, we were thinking of the height of the height of the curve as the number or frequency. Now we're thinking of the height of the curve as probability. That's the shift that we're making. We're shifting from this represents how much of a score exists to this represents how likely or how probable a score is. Scores that are the most common or most likely are in the middle. Scores that are the rarest or the least likely, if you were, say, randomly selecting a score, are out on the sides. Under a normal curve like this, 68.26% of scores, whatever that metric might be, are within one standard deviation of the mean. So let's say if I'm talking height, if I randomly select a person off the street, there's a 68.26% chance that their height will be within one standard deviation of the mean. Almost 70% of people are within one standard deviation of the mean. So most people are pretty close to the mean. If we go 2 standard deviations out, 95% of people, it's not exactly 95, but 95% of people are within 2 standard deviations of the mean. If I randomly select a person off the street, there is a 95% chance that that person's height will be within 2 standard deviations of the mean. If you go out to 3 standard deviations, which I don't think I have here, but if you go all the way out to 3 standard deviations, that you're up to nearly 100% chance. So a 99% chance that a randomly selected person would fall within 3 standard deviations. So now the height represents probability, and how far you are from the mean is how probable or improbable your score is. Lower z-scores that are close to the mean, so like 0.5 or 0.1 or negative 0.2, are much more probable and much more common. Bigger z-scores, like 3 or negative 5, are much rarer and much less likely. If you randomly select somebody, they're way more likely to have a z-score that's close to 0 than a z-score that's far from 0. So again, now we're no longer thinking of your point at the distribution representing how many of that thing there are. So how many, say, people who are 5'7" there are. Now we're thinking of it as how likely is it that if we randomly grabbed somebody, they would be at that point of the distribution. We're essentially doing this. We're essentially saying, okay, what is the probability of selecting somebody from that part of the distribution? So what's the probability of selecting somebody between a z of -2 and +2? 95%. The same logic. What's the probability of selecting a black square out of these 36 squares up here? Same logic. Just in case the parallel wasn't obvious enough, I've changed the colors so it looks the same. That's the logic that we are going to be using for the rest of this series of lectures. So I'm going to introduce you to something called the promise scale. So I said I'd be using both anime and psychology examples in here. This is one of those psychology examples. The promise scale is a series of scales, actually. It's a whole collection of scales that are often used in healthcare, and some of those scales are intended to measure things like mental health. So we're going to be using one of the mental health ones. The promise scale is handy. It's handy for teaching statistics because it's normed, which means that we know the population mean and the population standard deviation of this test. There's a bunch of different scales. They have scales for fatigue, emotional distress, pain, and physical functioning. Most IQ tests are also norm tests that have a known mean and standard deviation. Standardized tests like the ACT, the GRE, high school exit exams, all of those also have a known mean and standard deviation. When I say a normed test or a standardized test, all that means is that this test was created to have a specific population mean and a specific population standard deviation. And that's really useful for teaching statistics because we don't actually know the population mean or population standard deviation of most things. So we're going to be working with the promise scale a lot for the time being. I screwed up the animations here a bit, sorry. So let's say I want to know the percentage of people, or the probability of randomly selecting a person, you can think of it either way, with an emotional distress score on the promise scale of above 65. Essentially, I want to figure out what percentage of people have 65, or what percentage of people have 65 or less. I'm essentially calculating a percentile at this point. First, we have to compute the z-score for a mean of 65. So to find out how many people have a mean below 65, we need to figure out where 65 is on this curve. And we do that by a z-score. Remember, z-scores are a measure of distance on the x-axis from the mean. How far away from the mean are these people? And from there, we can use that information to calculate how many people fall in that part of the distribution. Now, the mean, the population mean for the promise scale is 50, and the standard deviation for the promise scale is 10. So just as a reminder, the formula for a z-score that we learned last time is z is equal to whatever score you're looking at minus the population mean over the population standard deviation. So let's start plugging things in. The score that we're interested in is 65. 65 minus the population mean, which is 50, divided by the standard deviation of the population, which is 10. 50 minus 6, or 65 minus 50 is 15, divided by 10. Our z-score is 1.5. I'm going to erase this because I actually have this animated out so it's easier to read because I know my handwriting isn't the best. So 65 is our score, minus 50, the population mean. So this tells us already that 65 is going to be above the population mean. Divided by 10, so we're converting that into units of standard deviation. 65 minus 50 is 15, divided by 10. Our z-score is 1.5. In other words, the standard deviation for our promised mental distress score of 65 is 1.5 standard deviations above the mean. Then we can use something called the z-table. So normally, if you want to find the area under a curve, so first I'm going to show you what this curve looks like. Here we have here we have all the possible scores on the promised mental distress scale. Their mean is 50. The score that we're interested in is 65, and it's about 1.5 standard deviations above the mean. And we're interested in how many people have a score above 65. So we're interested in this. We want to know the area under the curve, or how many people, or what percentage of people fall in this range. Now, normally to calculate the area under the curve, you would need to know calculus. I do not know calculus. I cannot teach you calculus. But luckily, other people have done the calculus for us. So we're going to use something called a z-table. We can use the z-table to look up the proportion of the total distribution in this range. So the total distribution adds up to 100%. If we know our z-score of a point on the distribution, we can look up the percentage of the total distribution that's to the right or the left of that number using a z-table. So if we do that, that'll give us an area of 6.68%. 6.68% of people are above that on the promise scale. I'm going to show you a z-table, though. I'm not just going to, tell you that. Here is a z-table. This is from a textbook, but if you just search for z-tables, and I think I do have a link somewhere in this lecture to a z-table I found online. If I don't, you can just search for them. There's a lot of them out there. But you can use this to figure it out. So the information that you need, first of all, is the z-score you calculate. And we found that a promise score of 65 has a z-score of positive 1.5. Then you need to figure out if you're looking in the body of the distribution, the tail of the distribution, or between the mean and the z-score of that distribution. As a reminder, the body is the bigger part of the distribution, and the tail is the smaller part of the distribution. The body includes the mean, the tail does not. If it helps, I'll draw my creature again. This is a distribution. The body is the big part, and the tail are these parts on the edge. Here's our creature. We're using cats. This is a very strange cat. Anyway, the body's the middle, the tail's the end. So we were interested in the percentage or proportion of people who have a score above 65. So that's above the mean. 65 is above the mean, and we want people above 65. So we want this part. And if you're trying to figure this out, I definitely recommend drawing out the distribution to try and figure out what's going on. So do you think we are looking in the body, the tail, or the area between the mean and z to try and figure out the percent or proportion of people above a z-score of 1.5? The answer is we are looking at the proportion in the tail. We are interested in the people, or the percentage of people who are above 65. We're interested in the percentage of people who are in this shaded area up here. So the first thing we're going to do is we're going to find the column that says proportion in the tail. There are 3 columns: proportion in body, proportion in tail, and proportion between the mean and z. I'm looking at the proportion in the tail. Let's zoom in again. We are looking in column C. And the next thing we need to worry about is our z-scores 1.5. The rows of the z-table represent different z-scores. And yeah, there's your distribution again. This is where we're looking. We are looking at a z-score of positive 1.5, and we want the proportion of scores that are above that. So we look in the proportion in the tail. We find the row that has a z-score of positive 1.5, and then we find where those two things cross over. That is the proportion of the total distribution in this area, or the percentage of people who have a score that is above that point. So we get 0.0668. We can multiply that by 100 to convert it into a percentage. 6.68% of people are above a z-score of positive 1.5. Or, sorry, another way of thinking about that, of course, is 6.68% of people, or the probability of randomly selecting a person with a promise score above 65 is 6.68% if you just randomly grab somebody off the street. All right, next. Now let's say, slightly different problem. Now let's say you administer this promise scale to 500 people. So you've given the promise scale to 500 people. How many of those 500 would you expect to have emotional distress scores over 65? Well, we have 500 people total, and we know that 6.68% of people have a score over 65. So we need to figure out what 6.68% of 500 is, and that will give us the number. So if we just multiply 0.0668 by the number of people, 500, we learn that 6.68% of 500 is 33.4. And because we're talking about people, let's round that to a whole number. We can say about 33 people out of 500 should have a promise score over 65. So we can use this to figure out how many people in a sample should have a score on something in a certain range. Now let's talk about range specifically. So before we weren't really talking about range, we were specifically talking about the probability of having a score above a certain threshold, or you could also think of it as below a certain threshold. Now let's talk about the probability of being between two numbers. So let's say I want to know the probability of randomly selecting somebody, so randomly pulling somebody off the street who happens to have a promise score between 65 and 70. Your first step is figuring out where those are on our distribution. So this is our distribution. The mean of the promise is 50. So we're looking at between 65 and 75. In both cases, we're above the mean, but we want to know the percentage of people who are in this part of the distribution, between 65 and 70. First, we have to calculate the z-scores. So just as a reminder, the formula for z-score is z is equal to whatever score you're interested in converting into a z-score minus the population mean over the population standard deviation. For the promise, the population mean is 50 and the population standard deviation is 10. This is always the case for the promise. They specifically created the promise so it would always have the same mean and standard deviation. So let's start with 65. We've technically already calculated this, but let's do it again. First, we plug in our score, x, which is 65. We're converting 65 into a z-score. 65 minus the population mean of 50 divided by the standard deviation of 10 gives us a z-score of 1.5. So 65 is 1.5 standard deviations above the mean on the promise scale. Then we've got to do the same for 75. We have to find out that z-score as well. So we plug in 75 minus the population mean of 50 divided by the population standard deviation of 10. The z-score for 75 is 2.5. So 75 is 2.5 standard deviations above the mean of the promise scale. So we want to know the probability of getting a z-score between 1.5 and 2.5. We're randomly selecting a person whose promise mental distress z-score is in that range. Which means that we have to go look up those z-scores on the table. So here's our table again, and we are interested in the percentage of people who fall in this range here, between 65 and 75, or between the z-scores of 1.5 and 2.5. So that means we are going to have to look up two z-scores on the z-table. First, you have to choose if you're looking in the proportion in the body, or the proportion in the tail, or the proportion between the mean and z. So body, for example, for 65, the body would be the proportion of people to the left of 65. Tail would be the proportion of people to the right of 65. And the proportion between the mean and z would be, so the mean of the promise scale is 50. The proportion of people who are between 65 and 50 on the promise scale. There's a bunch of ways to do this. I could find, say, the z-score, or I could find the proportion between in the tail for 65 and then subtract the proportion in the tail for 75. I can find the proportion in the body for 75 and then subtract the proportion in the body for 65. There's a bunch of different ways that you can find this area. Essentially, you're finding one number and subtracting another most of the time. The way that I chose to do it was I looked at the proportion between the mean and z for 75. So what proportion of people are in this range? So that green highlighted range. So I went to the proportion between mean and z column, and I found the row for a z-score of 2.5, because that's what 75 is. The z-score of positive 2.5, as we calculated on the last slide. And I found that 49.38% of people fall in this range. 49.38% of people fall between a 50 and the 75 on the promise scale, or a z-score of 0 and 2.5. Then I decided I would find the proportion of people in here, so I could factor that out. So I went to the proportion between the mean and z, and I found the row for a z-score of 1.5 that corresponds to a score of 65. And that proportion was 43.32. So this section of the distribution is 43.32%. So to find this area here, I need to take 49.38 and get rid of this 43.32. Once I do that, all that's left over will be the proportion of scores between these 2 points. So, did I delete that animation? I did. I'm actually going to have to do the math. Oh no. So let's subtract. 8 minus 2 is 6. 3 minus 3 is 0. 9 minus 3 is 6, and then 4 minus 4 is 0. So 6.06% of people have a promise score between 65 and 75. You can also think of it as the chances that I will randomly select a person off the street with a score between 65 and 75 is only about 6.06%. Or if I randomly threw a dart at this distribution, the chances that that dart happened to land in this area is only about 6.06%. The probability is only about 6%. Now let's do another example. Let's say, oh wait, was that? Yeah, that was literally what we just did. All right, one more. We want to know the probability of randomly selecting an individual with a promise score between 42 and 58. So, once again, our first job is to find the z-scores. So, we are interested in, once again, the mean of the promise scale is 50. Here's 42, that's below the mean, and then 58 is above the mean. We want to know the probability of if we grabbed a random person off the street, what is the probability that their score would be in this range? So first, let's find out the z-score for 42 and the z-score for 58. As a reminder, the formula for z is the score minus the population mean over the population standard deviation. The mean of the promise scale is 50, and the standard deviation of the promise scale is 10. So we start plugging those in. 42 is the first score we're looking at, minus the population mean of 50, divided by the population standard deviation of 10, gives us a z-score of negative 0.8. We know that 42 is below the mean, and the z-score is negative because 42 is below the mean. It is 0.8 standard deviations below the mean. Next, we calculate the z-score for 58, our upper bound of our range. We plug in 58 as our score, minus the population mean of 50, divided by the population standard deviation of 10, and that gives us a z-score of positive 8. 58 is 0.8 standard deviations above the mean. So we're 0.8 below on one end and 0.8 above on the other. Then we go to our z-table to find the probability of randomly selecting a person with a promise score in this range. So this time, this blue shaded area is the area we're interested in. Z-score between 42 and 58, or a z-score of negative 0.8 and positive 0.8. That's what we're interested in. In this case, there's a bunch of ways to do this. You could get a body and then subtract the tail in either direction. What I did in this case was I looked between the mean and z. So first, I decided to look up this area. And then I would look up this area, and then I'd add them together to get the total area. So I decided to go for the column between the mean and z. Then I looked up the row for the z-score of 0.8. Now you might notice that the z-table does not actually have a negative 0.8, and that's because this distribution is symmetrical. The area between the mean and positive 0.8 is equal to the area between the mean and negative 0.8, so it only shows for the positive numbers. Don't be distressed. It would be exactly the same. The proportion is the same. The proportion between the mean and a z of either positive or negative 0.8 is 0.2881, or 8.81%. So this area is equal to 28.81%, and because this is also 0.8 standard deviations from the mean, this area is also 28.81%. So we just have to add 28.81% below the mean plus 28.81% above the mean. That gives us, carry the 1, 16, 17. I'm so sorry if I make a math mistake here, by the way. I'm not great at math. I think that says that should be 57.62%. So the probability of randomly selecting somebody with a promise score that is within 0.8 standard deviations of the mean is 57.62%. You can also phrase it as the probability of randomly selecting somebody with a promise score between 42 and 58 is 52.62%, or 57.62%. That's how you use z-scores to determine the probability of, say, randomly selecting somebody in a certain range or above a certain threshold or below a certain threshold. Now, let's say you have z-scores and you want to go back to the original units. So let's say I know that 9.18% of the population's promise scores are below a z-score of negative 1.33. Let's say I want to find out what promise score is associated with a z-score of negative 1.33. Let's say a z-score of negative 1.33 on the promise are people who are exceptionally mentally healthy. They have exceptionally little mental distress. And I want to know what that threshold, that score on the promise scale exactly would be. I don't care about the z-score. I just want to know if somebody gets like a 2 or like a 12 out of however many on the promise scale, does that put them in this category? The formula to convert a z-score, or to convert a z-score back into the original units. So the formula for z-score is z is the score minus the population mean over the standard deviation. All we have to do to convert that back into the original units is solve this for x the original score. Or we can, just plug things in. So we know that we have a z-score of negative 1.33. We don't know what the original score is. That's why we're doing the math. We know that the population mean of the promise is 50, as it has been, and we know that the standard deviation is 10. So now we just solve for x. Let's multiply both sides by 10. That cancels out. So we get negative 10.33, or 13.30, I believe. Sorry, I told you, I'm not great at math. 13.30 is equal to x minus 50. Then we add 50 to both sides. Get x on its own. And then negative 13.3 plus 50 is 36.7. Gosh, I hope I did this math right. Oh, I did! 36.7, yes. So we've converted it back. We found that the probability, or a z-score of negative 1.33 on the promise scale corresponds to a score of 36.7 on the promise scale. And because we know the probability of getting below that z-score, we can also say the probability of randomly selecting somebody with a score of 36.7 or less on the promise scale is only about 9.18%. So now we can convert between z-scores and raw scores and back. Raw scores, by the way, are just scores that we haven't done any math to. They're raw. We have not cooked yet in terms of statistics. This is another way, by the way. If you don't want to solve for x, you can just write the formula for converting z-scores back into raw scores as z times the standard deviation plus the population mean is equal to that score. So you can also use that. It's mathematically the same. It's just the z-score formula solved for x. Oh, all right, a little longer. So let's talk about binomial distributions in probability. I'm not going to go over this too in depth because it's not super commonly used in the type of statistics we use for stats. I've done this kind of thing before, but it's not super common. Binomial data is data that only has two results. So yes or no, or the lights are on or the lights are off, or you passed or you failed. There's only two possible outcomes. For example, when you flip a coin, that's a binomial probability. You either get heads or you get tails. We're going to ignore the possibility that it lands on its side. Let's just say it's either heads or tails. Now, if you flip a coin 2 times, now you have 4 possible outcomes. So if you only flip it once, you have 2 outcomes, heads or tails. If you flip it in a set of 4, you have 4 possible outcomes. You could get heads both times. You could get heads the first and tails the second. You could get tails first and heads the second, or you can get tails both times. So what's the probability of only getting 1 head? Out of the 4 outcomes, there's only 2 where you get only 1 head. So there's a 50% chance of only getting 1 head out of your 4 coins. Or 50% of the chance, yeah. There's a 50% chance that if you flip a coin 2 times, you will only get 1 head. What's the probability of getting at least 1 head? So there's at least 1 head here, at least 1 head here, at least 1 head here. There's a 3 out of 4 chance that you will get heads at least once if you flip a coin twice. So essentially, we are taking this binary outcome. There's only two possible outcomes. And by creating sets of trials, so flipping a coin twice or flipping a coin 10 times, we can kind of make it into something resembling a normal distribution. Oh, we got 5 out of 7 heads. Or 5 out of 10 were heads. 3 out of 10 were heads. 9 out of 10 were heads. We essentially can turn it into a more continuous distribution. So, yeah, what's the probability of getting 2 heads in a row? Well, there's only one outcome where we get 2 heads in a row, so it's only a 25% chance. And by stacking these sets of trials, you can essentially create a normal distribution. So let's say I flip a coin 10 times and I measure how many heads I get each time, and I do this a lot. Let's say I do it 10 times. Eventually, I should get something that looks like a normal distribution. Most trials, I get 5 heads and 5 tails. Some trials, I get all 10 heads. Sometimes I don't get a single head. And then as you go on, eventually it forms a normal distribution that you can calculate probabilities on. So essentially we're recreating a continuous measure out of a measure that only has 2 possible outcomes. It's kind of a weird thing. It is used in statistics, but it's not super common in psych statistics. Like I said, I've done it, but you may never do it. So, why are we talking about this? Well, as psychologists and as researchers in general, researchers are usually interested in what we call significant differences. We want to know if, say, 2 groups are different, say a treatment group and a control group. But we've talked about earlier, there's something called sampling error, right? No population is ever going to be exactly the same as it's a sample from that population. And 2 samples are never going to be identical to one another. We know that the average of, say, this group of 10 people will not be the same as the average of this group of 10 people. It's highly probable that there will be some difference between those 2 sets of 10 random people. So we know that the average height of group A is probably going to be different than the average height of group B. Or if we're talking psychology, like say we're trying a new therapy for depression, the average level of depression in group A is probably going to be different than the average level of depression in group B, regardless of whether our therapy or medication does anything, just because that's how samples are. No group, 2 groups of 10 people are exactly the same. So we know these numbers are going to be different even if our therapy or our medication does nothing. So we want that difference to be so big that it's extremely unlikely that we got it due to chance. Because we know 2 samples are going to be different just due to random chance. We want to be extra sure that this isn't just a matter of random chance. We want it to be very unlikely that this would occur due to random chance. Now, 95% of outcomes, based on what we've learned, will fall within a z-scores of plus or minus 1.96. 95% of the time, random chance will put us within 1.9 positive to negative 1.96 of the mean. So the difference in depression between those 2 groups, 95% of the time, assuming that we didn't do anything to make them different, should be pretty close to the mean. The probability of getting a z-score above positive 2 or below negative 2 is very, very, very low. There's a less than a 5% chance that we would just randomly find a difference that is that big. Either one group is that much higher than the other, or one group is that much lower than the other. It's highly improbable. So as psychologists, we've determined, and scientists in general tend to follow this rule. I read a biology paper earlier today that followed this rule too, so it's not solely psychologists. We say we think that it is highly unusual if something happens when there's only a 5% chance of it happening. We say, if there's only a 5% chance that this is a fluke, that this is error, that this is some kind of coincidence, we think it's more likely that something's actually going on here. If there's only a 5% chance that that flashlight would have flashed in response to my question just randomly, we think it's more likely that something made it flash, if we're talking in terms of like ghost hunting. So what that looks like, let's say I'm trying to determine if my friend has given me a coin that's weighted. So let's say we do a coin flip to decide which one of us gets to take shotgun on a road trip, like who gets the passengers and who has to either, say, drive or sit in the back seat. Let's say I want to figure out if the coin is weighted. I want to figure out if my friend is trying to cheat. Of course, there's a wide variety. Let's say I flip a coin 50 times. There's a wide variety of the number of times it might come up of heads. Most of the time, it'll come up heads about 25 times out of 50. It's very, very unusual that it would come up heads 50 times in a row, and very, very unusual that it would come up heads not at all. It comes up tails 50 times in a row. So, I can determine the probability of those things happening. The z-score of getting heads 36 times out of 50, or more than that, is 1.96. And there's less than a 2.5% chance of that happening. There's less than a 2.5% chance that I would get 36 or more heads out of 50 flips. And there's also a less than 2.5% chance that I would have gotten, say, is this 15 or fewer heads out of 50 flips. So as a psychologist or as a scientist using this 5% rule, I would start to be suspicious. I would start to think, this isn't just bad luck or good luck on my part. This coin is probably weighted. If there's a less than 5% chance that I would have gotten that result with an unweighted coin, does it guarantee that the coin is weighted? No. Like, it is totally possible for you to randomly flip a coin 50 times and get it heads 50 times in a row. All of those events are independent. It is possible that that could happen. It would be very unusual, but it could. But at the point where there's less than a 50% or less than a 5% chance of that outcome, we get suspicious of it. We think there is something going on here. By using this sort of rule, decision rule, I would say, let's say if we flipped the coin 50 times and we got 44 heads, I would say, based on this 5% chance rule, this coin is weighted. You are cheating. The most likely explanation is that you're cheating. It's very unlikely that this was due to random chance. That's the kind of thinking that we're working with. And we apply that to studies. So there's less than a 5% chance that the depression in this group would have been that much higher than the depression in the control group or in the treatment group if the medication did nothing. We use this essentially to say, we know these groups are different, but are they different enough for us to conclude that something actually is happening? That's where probability fits into this whole thing, and how probability fits into testing hypotheses and doing studies and creating knowledge. Let's do a bit of a review based on that. Let's say the Hero Commission measures how hard Saitama can punch. Saitama's punching strength is 3 standard deviations above the mean strength of the other applicants to the Hero Foundation, or the Hero Commission. 3 standard deviations, according to the cutoff that we have in psychology and other sciences, is 3 standard deviations considered significantly stronger. Remember that significant cutoff. The answer is yes. Remember, there's a less than 5% chance of something happening if it is more than 2 standard deviations, well, 1.96 standard deviations away from the mean, but if it's, let's round to 2, if it's more than 2 standard deviations from the mean, there's less than a 5% chance of that. There's less than 5% of people would have a punching strength 2 standard deviations above the mean, or 2 standard deviations below. Saitama's punching strength is 3 standard deviations above the mean. He is clearly unusual. He's absolutely past that cutoff of 1.96. We would consider that in psychology and in other sciences significantly stronger. It's probably not a fluke. There's probably something special about him. Here's another one. Tokiyuki competes in a race. His time is 1.5 standard deviations below the mean time for completing the race. Remember, this is a race. You want to be faster. You want your time to be smaller. 1.5 standard deviations below. According to that cutoff, did Tokiyuki finish the race significantly faster than the other runners? Nope. Remember, the cutoff is he has to be further than 2 standard deviations from the mean. 1.5 standard deviations below the mean is still within the realm of what we would consider sort of normal error. There might not be anything particularly special about Tokiyuki. He still seems fairly average. We could have just happened to randomly pick some person who's a bit faster than average, but not unusually so. So, that is probability. And if you have any questions about any of the things that I've just talked about, I am more than happy to take them now. I'm not actually sure if I have any people actively watching right now. So if you don't have questions, that is also okay. Okay. Don't know. Well, if there are no questions at this particular moment in time, but if you come up with one later, or if you're watching the VOD and you have any questions that you'd like me to clarify, or if I said anything confusing or anything like that, feel free to drop it in the comments section below, and I will get back to you as soon as I possibly can. I hope that you are having a good day today. Take care of yourself. Make sure to get some rest somewhere in there. And I will see you. Oh, we'll see you next class when we are going to be talking about probability in samples. Today we're talking about probability specifically in populations. Wednesday, 7:30 p.m. Eastern Time, we'll be talking about how probability applies to samples. All right. Take care, everyone. It was great having you here, and I will see you next time.